Today, I'm going to talk on development and testing of ultra high performance concrete for durable bridge components and connection. This project is funded by Transportation Infrastructure Durability Center, which is commonly known as TIDC. Let's start with motivation and objective. Increased traffic loads have given rise to the need of bridge structure with increased load resistance. Due to increased traffic flow, disrupting the traffic has higher economical impact. Thus, we need quicker construction, which is possibly by utilizing the concept of accelerated bridge construction, also known as ABC technology. At the same time, we need to have bridge structure with enhanced durability and reduced maintenance. The aging of our infrastructure is critical at this point, where 42% of the bridges are at least 50 years old and 7.5 of nation bridges are considered structurally deficient as per ESC report card 2021. Thus, there is a general need for bridge structure with enhanced sustainability and lifespan. One of the objectives of this research is to develop the cost-efficient, non-proprietary, ultra-high performance concrete mixes that can be used for bridge construction, like casting connection that we can see in the picture, or the bridge deck or bridge girders. So why UHPC? Most of us already heard about UHPC. It is a cementitious composite with relatively high amount of binder in comparison to conventional concrete. It is designed to use a water to binder ratio of less than 0.2 or its compressive strength in excess of 150 megapascal or say like 22 psi. The addition of tailored discontinuous fiber reinforcement leads to significantly high ductility and durability of the cracked composites. The key for the strength and durability properties is a very high packing density of the matrix. The properties of UHPC are very exciting and its application in bridge construction has a great potential to address the current and future needs of health of aging infrastructure in the United States. Our research approach includes following steps. First, identifying suitable material suppliers in the New England area because we want to use the locally available materials. Second, selecting the suitable materials for the matrix. Third, applying the UHPC principle in the mix design and mixing process to enhance the matrix density. Fourth, performing experimental investigation and material characterization. Then tailoring the concrete matrix based on the efficiency factor. It takes account of compressive strength, workability, and cost. It gives more weight to the compressive strength and less weight to the spread. After after selecting the suitable matrix, we select the suitable fibers and emphasis being placed on the fiber efficiency, workability, and performance of the composite. As fibers are the most expensive ingredients in the UHPC. In the first phase of pest investigation, we use the resonance frequency mixer because it provides high mixing consistency at short time and quality of particle dispersion without the use of any mechanical mixing tool. To the right, there is a graph of acceleration versus time, which is complemented by the picture shown underneath. From it shows like change from wet particles clumps to an homogeneous UHPC paste mix. Due to the limited mixing volume, mini flow cone has been designed and used for measuring the spread. When mixing UHPC, we usually use the tabletop mixer displayed here and follow the strict mixing protocol for enhanced consistency. The workability was measured by regular spread cone. Compressive strength has been tested using 2 by 2 inch cubes. Prior to testing, the load surface were grounded until passing the quality control. We check the surface smoothness with the straight edge and gauge filler because we do not want any roughness in the loading surfaces, which can lead to misleading compressive strength. Rotating ball bearing loading platen were used for testing the cubes in compression at a loading rate of 40,000 pounds per minute. Tests usually run from 2.5 minutes to 4 minutes. Without fiber reinforcement, the cubes fell explosively. The addition of sufficient steel fibers changed the failure mode from brittle to ductile, as you can see in the picture to the right side of the slide. For the direct tensile testing, dog bone shaped specimens were used with embedded mesh reinforcement at both the ends to make sure that the specimen fell at the middle. Here, the embedded end reinforcement has been placed on the fetched specimen to illustrate the location of the mesh. The test setup has been significantly improved to provide rotational freedom to the specimen pointed by the red arrow on the top and bottom, as well as we are able to get reliable deformation measurement. As a result, the displayed test results show very high consistency and quality, which is usually challenging to obtain. This is the improved single fiber pull-out test setup for the investigation of fiber efficiency. You can see there is a red vertical line to illustrate the embedded fiber. A load cell measures the pull-out load while an LVDT on the right side measures the fiber slip. This setup has successfully been tested and more tests will follow like in future to characterize the bond between fiber and UHPC matrix. In terms of durability properties, we have started to test UHPC surface resistivity, which is indicative of the pore structure and the permeability of the matrix. We also have started to test UHPC DIMS in the phase thaw table. Another parameter to pay attention is to the amount of entrapped air. We have used two approaches. First, mini air meter to measure the total air void contained in the fresh concrete, and second, filling the air voids of the ground UHPC surface with white powders, as we can see in the picture on the right hand side. Then followed by the digital photo analysis. Then the air voids have been linked to the compressive strength and found out that there is a linear correlation between compressive strength of the mixes with different air content. Basically, this research has been broadly divided into two parts. First, we started with the pest investigation, followed by the UHPC concrete investigation. We did more than 60 pest mixes, usually small in volume, like 0.16 liter, mostly mixed with the resonance frequency mixer with water cement ratio of 0.23 to 0.25. We started with our house UHPC mix as a reference mix using white cement, white silica fume, silica powder, silica sand, and high range water reducer. Then we replace several material in constituents one at a time. For example, changing the type of cement, type of supplemental materials, which includes fly ash, glass powder, slag, and switch to basalt aggregates. Those are locally available here in New England area. We have analyzed those results and based on the E factor, which takes account of compressive strength, workability, and cost, an optimized test has been finalized. Once we finalize the optimized test, we move towards the actual UHPC matrix. We mix like around 50 UHPC concrete mixes at a volume of 2.1 liter each time with water cement ratio 0.23 to 0.25 and aggregate to cement ratio from 1.2, 1.5, and 1.8. Aggregate particle distribution was tailored to follow the modified Anderson and Andreasen curve. In terms of fiber reinforcement, we started to add fibers in the volume fraction of 1%, 0%, 1%, 1.5%, 2%. And we use different kind of fibers. Some are like smooth fibers, some are rock in surfaces. Some have length of 13 millimeter and some are like 19 millimeter. But all of the fibers are available in US to comply with the American Buy Act. Here, I like to show some of the results. For example, you can see the effect of cement replacement by slag. We can see that all the mix has exceeded the compressive strength of 150 megapascal while having sufficient workability like more than 270 millimeter every time.
So it's 3 minutes, Bihaya.
I'm sorry. Okay, I will try to finish it fast. This has led to decrease. Addition of slag has led to decrease in the workability, starting with the 40% replacement In terms of silica film to cement ratio, at the bottom right, you can see the best workability and strength at 20 at the ratio of 20%. Here you can see the effect of adding more aggregates and fibers on the workability of the mix. As the spread decreases with the increase in the aggregate to cement ratio, more aggregate you add, the more you lose the workability. A similar trend is seen with the addition of fibers. The more fibers you add from starting from 0, 1, and 2% fiber volume fraction, more you lose the workability. This diagram is an excellent indicator that how change in the aggregate to cement ratio can be used to offset the effect of added fiber reinforcement. For example, if you like to have 270 millimeter of spread, and aggregate cement ratio should be 1.7 without having any fibers in it. But if you want to add 2% of fiber, then aggregate cement ratio should be limited to 1.3 and still achieve like same spread value. Here are some of my preliminary results that I obtained from direct tensile test and the single fiber pull-out test. Both results are very promising. The direct tensile test shows great consistency, strain hardening behavior or tensile strength of up to 2 psi and ductile behavior indicated by peak strain of more than 0.5%. The pull-out results show high load resistance and shear strength hardening. This is seen by keeping the pull-out load almost constant, although the fiber is being pulled out and thus steadily reducing its embedment length. We are in the process of doing like more tests in the future. Last but not the least, uh, here we can see the preliminary results from the electrical resistivity. There is a threshold for low permeability concrete of like 27 kilo ohm centimeter, but we have achieved that threshold value only in like 4 days, and we keep measuring the resistivity value until it reaches the detection limit of the equipment. It's 1,000 kilo ohm centimeter. This means that the pore structure is extremely densified. It is acting like a rock. Um, and this is the key property for long-lasting durability of this material. So, following conclusion can be drawn from this research up to now. We successfully developed the UHPC mixer design using locally available materials and obtained promising workability results, mechanical properties, and durability properties. We want to further continue to enhance and improve specimen preparation and testing methods for more consistent results. In the future, we plan to investigate the durability properties and study the fiber efficiency, perform more cost analysis, and transfer knowledge to UHPC technology to local precast companies. I would like to express my gratitude to the following centers, departments, schools, companies for their support. It includes TIDC, Condor, IMS at Uton, Lafarge Holcim, Still Light Concrete, Fibercon, Baker Fiber, Hyperfiber, Lehigh Cement, Lehigh White Cement, Norchem, Boral Pliers, Kilcon, ACMC, and School of Engineering at Uton. Also, I want to thank to my colleagues Chris and Dog and undergrad students Sydney, Jay, Ethan, Corey, Dom, who supported this research despite the challenges due to COVID-19. And finally, thanks to my advisor for the constant guidance to make this research successful. Thank you everyone for listening to my presentation.